X-rays. X-rays are produced using apparatus something like this. We have a filament powered by a low voltage supply and a high voltage supply between it and a copper anode, on the front of which is a tungsten target. The copper is there to dissipate the heat produced. Electrons are emitted from the heated filament by thermionic emission. Then the electrons are accelerated through the large potential difference, and when they hit the tungsten target, they produce X-rays. I'll just demonstrate that now. So an electron is released, accelerates, hits the target, produces an X-ray. Once again, released, accelerates, hits the target, produces an X-ray. And once more. There are two distinct ways that the X-rays can be produced. There's Bremsstrahlung radiation caused by the rapid deceleration of the electrons, and these X-rays can have a range of wavelengths. Also, there are characteristic X-rays. These are produced when the electrons knock out electrons from the inner shells of the metal target. Electrons then quickly drop down from the higher energy levels, emitting precise wavelength X-rays. So if we plot a graph of intensity of X-rays released against the wavelength of the X-rays, we'd get something like this, with this continuous spectrum, the Bremsstrahlung radiation, and peaks due to the characteristic X-ray radiation. This diagram shows the main components involved with producing an X-ray image. We have the machine, which is producing the X-rays. These are then passed down through the area of the body we need an image of and hit the photographic plate. The more X-rays that pass through, the greater the photographic plate is exposed. So areas of bone would have less exposure and appear white on the photographic plate. Areas of soft tissue would stop very few X-rays and would appear black on the photographic plate. Here we have a filter. This removes the lower energy X-rays, which would have a greater chance of being absorbed by the body, causing damage to the body. And here we have a lead grid. This removes any diffracted or scattered X-rays, such as these two rays here, which would otherwise blur the image being produced on the photographic plate. Only the X-rays passing vertically down can get through the grid. Bones absorb far more X-rays than the surrounding soft tissue. The bones therefore produce a shadow on the photographic plate. X-rays are absorbed by electrons, and so the more electrons an X-ray meet on its journey, the weaker the emergent X-ray beam will be. The number of electrons depends on the density of the material, as in bone is more dense than the surrounding tissue, the number of electrons per atom, which is linked to the atomic number, and the thickness of the material it is passing through. To obtain information about soft tissue areas is more difficult, as there will be little or no difference in the level of absorption of the X-rays. A contrast medium can be used to overcome this problem. To obtain images of the digestive system, patients can be given a liquid to drink containing barium sulfate, which absorbs X-rays. This is known as a barium meal. Allowing different time intervals between ingestion and taking the X-rays allows different parts of the digestive system to be analysed, as the barium meal passes through the body. The heart and circulatory system can be imaged in a similar way by injecting a dye containing iodine, which is opaque to X-rays, into an artery. The image produced is called an angiogram. A number of other contrast media are available, which can be used on other parts of the body. X-ray images are produced by the body absorbing some of the energy of the X-rays. There is some risk involved in this, as the X-rays are ionizing radiation, and so the X-rays used will be as low energy as possible to obtain the required image. These small doses pose a minimal risk to the patient, and the benefits generally far outweigh the dangers. the radiographer will be involved with many X-rays every day, and so could be exposed to a dangerous dose. For this reason, they leave the room or stand behind a protective screen during the procedure. Unborn babies are at a slightly increased risk from X-rays, and so, if possible, a different imaging technique, such as ultrasound, would be used on a pregnant woman. If an image was required of the arm, for instance, the pregnant woman could wear a lead apron to protect the womb. If an X-ray of the womb area is essential, then an X-ray can be taken, but the radiographer would use an extremely low dose. In some cases, moving images would be very useful, but the high dose of X-rays needed would make this too dangerous. With the use of image intensifiers, however, extremely weak X-rays can be used, allowing prolonged exposure without a dangerous dose. X-rays generally produce clearer images than ultrasound and are more penetrating, so are more able to image deeper structures within the body. You can obtain an X-ray of a whole chest, whereas ultrasound images cover a more limited area. X-rays can be harmful, however, so exposure must be limited. Ultrasound imaging is not believed to pose any danger, and so moving images can be obtained over a longer time period.